Welcome to The Explainer. Today, we're going to pull back the curtain on the hidden architecture that powers pretty much every major AI platform out there. This thing is the secret sauce that stops the entire world of AI from just, well, descending into total chaos. Okay, so let's start with a problem that every, and I mean every AI team faces. You're building a complex model, right? You've got dozens, maybe even hundreds of different steps that have to happen in a very specific order. So how do you manage all that without everything just completely falling apart?
Because, without some kind of system, this is what happens. Workflows fail halfway through. Data gets totally corrupted because one little step ran out of order. And trying to debug it, it's an absolute nightmare. It's a mess, unpredictable, impossible to scale, and you can't rely on it.
But here's the thing. There's this incredibly powerful and, honestly, kind of elegant solution to all this. It's called the Directed Acyclic Graph, or what everyone in the field just calls a DAG. This is the blueprint for bringing order and rock-solid reliability to AI.
So, how does it work? What's the magic behind it? Well, the really cool thing about a DAG is that everything you need to know is literally in its name. If you can just get your head around 3 words, directed, acyclic, and graph, you've pretty much understood the whole concept.
Okay, think of it this way. A DAG is basically just a recipe for your project. It lists all the steps, we call them tasks, and it makes the dependencies between them crystal clear. It's common sense, right? You can't frost the cake before you bake it. And in our world, you can't train a model before your data is clean. The order is everything, it's non-negotiable. Okay, first up, directed. This just means every connection is a one-way street. The workflow has a mandated direction, a strict sequence. Task A has got to finish completely before Task B can even think about starting. No shortcuts, no ambiguity. Next, we have acyclic. And honestly, this is the real lifesaver here. It just means the workflow can never, ever loop back on itself. It always moves forward, from start to finish. And that guarantees that it will, eventually, end. This simple rule prevents the whole system from getting stuck in a crazy infinite loop, burning up resources forever. And last but not least, graph. This is just the map itself, the big picture. The tasks, the actual jobs to be done like clean data, those are the nodes. And the arrows connecting them, the ones that show the dependencies, we call those the edges. Put them together, and you have your blueprint.
All right, let's see this in action. It's super simple. So you've got one task, a node, let's call it clean data. Then you've got another node, train model. The edge is just the arrow that connects them, and that arrow is the rule. It says, hey, you can't do this until that's done. It's visual, it's simple, and most importantly, a computer can execute it perfectly every time.
And this all leads to the one single golden rule of DAGs: no loops. Ever. A workflow can never return to a step it has already finished in the same run. Now, if a model needs retraining, you don't just loop back. No, you trigger a brand new, clean run of the entire DAG. That discipline is what gives you reproducibility and stability.
Okay, so that's the theory, which is cool and all, but let's get real. How does this apply when you're building an actual machine learning model from the ground up?
You'll see that the entire journey of a model, from start to finish, is a perfect DAG. First, you got to ingest the raw data. Then, of course, you clean it up and normalize it. That clean data is then used to engineer features, which get fed into the model training task. The model that pops out gets evaluated, and only, and I mean only, if it passes our tests does it get deployed. See? Each step is a node, and the flow of data creates the edges.
So you have this beautiful blueprint. Now what? How do you actually make it run? Well, you don't just draw it on a whiteboard and hope for the best. You use these incredible tools called orchestrators. Think of them as the conductor of the orchestra, making sure every part plays at exactly the right time.
Now, not all orchestrators are the same. They each have their own personality, their own philosophy. You got Apache Airflow, that's like the battle-tested Swiss Army knife. It's super flexible and great for all kinds of data jobs. Then there's Kubeflow Pipelines, the cloud-native specialist. It's built for running massive, containerized machine learning workloads on Kubernetes. And then you have some newer tools like Dagster, which are obsessed with data itself, tracking its lineage and quality as it moves through the pipeline.
Which really brings us to the big question, right? Why? Why has this one specific pattern, the DAG, become the absolute king in the world of AI and MLOps?
Well, it all boils down to a classic battle: control versus chaos. With the DAG, you get centralized control. A single conductor, your orchestrator, sees the whole plan. If something breaks, you know exactly where to look. The alternative is this decentralized approach, sometimes called event choreography. It could be scalable, but man, it can be chaotic. Trying to figure out what happened to your data from start to finish is nearly impossible. And for serious AI, that's a total non-starter.
And this is why DAGs are the absolute bedrock of modern MLOps. It's not just a nice to have, it's essential. You get reproducibility, so you can rerun a workflow and get the exact same result. You get auditability, a clear, traceable log of every single thing that happened. And you get governance, which you need to make sure only high-quality, validated models ever see the light of day in production.
So, at the end of the day, what's the big takeaway here? The DAG isn't just some techie diagram. It's the operational blueprint. It's the common language that lets data scientists, engineers, and the business side of the house all work together to build something that actually works and works reliably every single time.
And that leaves us with a really mind-bending thought about where this is all going. Right now, we humans are the architects. We build these DAGs. But what happens when the AI gets smart enough to start building and fixing its own DAGs? We're heading toward a future of self-optimizing systems that can reroute around failures and adapt on the fly. The blueprint itself is becoming intelligent.